Hello?
Hello, can you hear me?
Uh, I can hear you. Can you hear me?
Yes, yeah, loud and clear. Thank you for
Okay.
joining.
Okay. No
Um,
problem. Did you
yeah,
happen to get my email by any chance?
yeah,
Uh,
yes, yeah. I just I read your email, and yeah, thank you for the two questions. That
okay.
is really helpful.
Okay.
Yeah, hopefully, I know we have around 10 audiences today.
Okay.
Uh, yeah, so usually, we have to strive to invite more audiences,
hmm
but this time, no. I could not upload the flyer for a while. So after I uploaded it, and then we had only 2 weeks uh, before the webinar. So it was, I think, too short to
Okay.
invite more people.
Okay.
Um, yeah,
Is I could invite non-IEEE members, correct? Or
that is yeah totally fine.
okay.
Any non-members from other countries are also accepted.
Okay.
Yeah, but this time it is really challenging for European guys because the time is almost midnight.
Oh, okay.
Yeah, I have lots of friends in European countries like Spain or Germany, um, yeah, Cyprus, whatever. So let me start sharing yeah, I just created, let me share this one. And my idea is to just start a slideshow.
Okay. I see the concept and the speaker.
Yes, yeah, we have only 2 slides.
Oh,
And then I repeatedly indicate the 2 slides so that the audience can get to know exactly what time that we start, and also the potential, the topic of the webinar, and then also the author's bio. That will be good for audiences.
okay. So no visuals at all for this one?
No, just
Okay.
just just 2 slides.
I see. Okay.
Um, yeah, so the topic is more like, yeah, if I understand correctly, he is gonna talk about um how to say, the contrasting the conventional simulation platform and then also the new type of platform with the digital twin technologies.
hmm Yeah, I did a little bit of research about it and some of the difference between traditional simulation and this new one that integrates AI and machine learning. Uh,
Mm.
it's pretty much simulation, but in real time almost, taking the feedback from the system, and there's a direct connection, real time connection. Um,
Yeah, I think yeah the Dr. Chen Shen can cover this topic as well. But the modeling is really challenging because condition is always changing.
mhm.
So when we identify all of the perfect model, I think that it is too late.
Yeah,
That is
it's
one thing.
is it even possible to really accurately
Yeah, and then
model it?
also there are lots of like unknown factors in the grid. Like
hmm
for example, synchronous generators are kind of like very fixed uh how to say the component. So we can know almost everything.
hmm
But the customer side is completely challenging. It's very difficult to get to know the situation because we do not know how many customers are connected
hmm
and what type of customers are connected. It's quite difficult to know them. And then the load characteristics is also, we have to identify, but it's really challenging. So,
Mhm.
oh, I see Chen Shen in the, so
Hi, Koji. Can you hear me?
yes, yeah, I can hear you. Good morning. Yeah, thank you very
Nice
much
to
for,
see you
yeah,
on the
good.
web.
Yeah, thank you so much for waking up really early in the morning.
Yeah, that's okay. It's
I
time to
re
get up.
Yes, I really appreciate it. How are you now?
Pretty good, but this semester is very busy.
Oh,
Mm.
I see.
When did you go to the US to be a professor?
Not a professor, but yeah, I'm currently a postdoc at UC Riverside. And then I came here in 2018. So I
Oh,
quit the Japanese EPRI in 2018. Actually, when I came to the US, still I was a researcher at Japanese EPRI. And then when
oh,
I got the degree in Upper Michigan, and then I decided to quit the Japanese EPRI and then started to work in the US.
great.
Are you involved in any like a new Sigre working group now?
Not yet, no. Currently, I'm too busy here. So I didn't aim to participate in secret work group.
I see. Yeah, it was great to work with you during that time.
Yes, I also I learned a lot from you. That's great. Thank you for inviting us to Japan to visit your institute.
Oh, yeah. That was a great moment for me as well. But unfortunately, I think it was not the perfect season for celebrating the cherry blossoms, I guess, if I remember correctly.
Mhm. So you're welcome if you have time to visit Beijing. I'll show you around.
Oh, thank you so much for your kind offer. Yeah, I still remember the very good moment at the university at that time. Yeah, but I'm getting older and older, so I do not have any energy for any kind of hikings with Xiaohuis. But yeah, it was nice. And then also, yeah, you have a very nice, the nature, beautiful garden inside your campus. I still
Mhm,
remember, yeah, good moment in your camp on your campus.
mhm.
So, do you need to check how your slide works well beforehand?
Oh, okay. Let me
So in
try.
this case, I will stop sharing here.
Hello, hello, Dr. Chen. Sorry, I'm trying to turn on my camera right now so you guys can see me. So give me a second. Sorry. Okay.
Let me see how to share.
So there is the button here
Yeah,
at
I
the
find
bottom.
the button.
Okay.
Can you see my slide?
Yes, yeah, I can see
I
the
can also
PowerPoint
see.
file.
Okay.
Okay.
I just heard you're discussing about how to realize digital simulation to power systems. Yes, there do exist a lot of challenges.
Mm,
Today, I mainly introduce the tool we my team developed uh, to uh, to conduct digital twin practice. Um, we do had some programs in industry to practice the digital twin idea. But unfortunately, the program, the materials are in Chinese. But anyway, I can give you a brief introduction
Yeah, sure.
about those programs.
Yeah, that would be nice. Yeah, because any practical yeah, the challenges are really appreciated.
Actually, there's a lot of programs about digital twins are conducting in both State Grid and China Southern Grid. They try very hard to see if the digital twin technology can help facing many challenges, such as online DSA, I mean, dynamic security assessment, some emergency controls, and many other things.
I see. So when I visited the China April, I remember that you also started to examine the co-simulation, like the combination of EMT simulation platform and then also the phaser or RMS simulation tools. So did you successfully combine the simulation platforms and then the
Yes,
cover?
well, yes, they have finished that program, and maybe next week, they will have a conference to show their results. We have also, I mean, my team also did something about
Okay.
combine different platform together to conduct some online simulation. For example, we have we have done a practice.
Okay, so let's get started. Good afternoon, good morning, good evening, everyone, depending on the locations. I'm Koji Yamashita, the moderator of this webinar. Welcome to the IEEE Foothills section. Our Foothills section covers a wide geographical area stretching from West Covina to the eastern end of California and from Temecula to Baker. Today, we have a speaker, Professor Chen Shen from Tsinghua University. Welcome to the IEEE Foothills section. Before starting your presentation, let me introduce you. Dr. Chen Shen, a senior member, received the BE and the PhD degrees in electrical engineering from Tsinghua University, Beijing, China, in 1993 and 1998, respectively. From 1998 to 2001, he was a postdoc research fellow with the Department of Electrical Engineering and Computer Science, University of Missouri, Rolla, Montana, USA. From 2001 to 2002, he was a senior application developer with ISO New England, Massachusetts, USA. Since 2009, he has been a professor with the Department of Electrical Engineering at Tsinghua University. He is currently the director of the Energy Digitalization Research Center, Sichuan Energy Internet Research Institute, Tsinghua University. His research interests include power system analysis and control, renewable energy generation, and smart grid. He is the author or co-author of more than 200 technical papers and one book, and holds more than 50 issued patents. Wow. Everyone, the digital twin is going to be a hot topic in the near future, and Dr. Shen is going to cover this exciting topic today. Well, Chen, fire away.
Thank you, Koji. Thanks everybody for participating this webinar. I'm very glad to share the ideas and some practices with you about the digital twin. Okay, I'm gonna turn off my camera. So maybe in case the internet net is not very stable. Let me turn on the presentation mode. Today, I'm going to go through those topics. We start from the new requirements for simulation tools proposed by the research of new power systems. In China, we call the system with high penetration of new power generation and high penetration of power electronic equipment, double high system or new power system. The new power system have many new characteristics, such as the system inertia has decreased, so the system is easily susceptible to disturbances. The unit capacity has become smaller. As traditional units, you often have hundreds or even thousands of megawatts, while new energy units typically only have a new megawatts or at most a dozen megawatts. That pose great challenges to simulations when constructing cases. Also, the system has stronger special temporal coupling because HVDC transmission lines here in China, there are so many, dozens of them, which transmit bulk power from the west to the east. Those HVDC lines easily propagate the impact of force across multiple timescales to a wide area. The system has more complex and diverse dynamics due to the different control of power electronic devices. And the system is more fragile due to the fragility of power electronic devices. Unfortunately, we are lacking of tools to analyze and control new power systems. Yes, we do have some theoretical tools, but they only applicable to simple system to explain the theoretical foundation of power system to students. That makes us heavily depend on simulation tools. We usually go through the 4 steps to use a simulation tool. First, we choose the appropriate simulation tool according to our research goal. Then we build models for the simulation object and set parameters. Then we choose a simulation scheme, such as the time step, and run the simulation tool. Then we collect the simulation results and analyze the results. For traditional power systems, because the dynamics are mainly determined by synchronous generators, the electromechanical simulation tools are usually used. However, for the new power system, because more and more power electronic devices join in and their dynamics are much faster than those of synchronous generators, electromagnetic simulation tools are necessary. Because the source of randomness in traditional power system are not many, randomness can be dealt with by scanning a finite number of cases. However, exhaustive scanning is difficult to cope with the dramatically increased randomness in new power systems. Frankly speaking, today's power system simulation tools face a lot of challenges. First, it's hard to construct simulation cases. Because system scales become larger and larger, system models and parameters are more and more complex. Due to privacy preserving requirement, white box models of new generation devices are more difficult to build. I don't know, this is a situation in the US. But here in China, the wind turbine generator manufacturers, the PV generator the manufacturers, they are reluctant to share their white box models to operation departments. So it's hard to build the system cases. Second, today's simulation tools have unsatisfactory simulation performance due to the stronger stiffness of the new power system. Numerical stability problems are more and more prominent. Small calculation steps need to know computational efficiency. Third, due to lack of standard cases, unified verification computing platform, mechanism, and technical support means for sharing results, it's hard to conduct comparison validation. All those reasons impede the progress of scientific research. The new requirement for the power system operations also pose new requirements for simulation tools. Traditional power systems actually have relatively to new power systems, special temporal coupling dynamics. That's the reason why the operational functions of the power system are broken down into several business segments, each overseen by different departments. Also, this can be roughly proved by the fact that different simulation tools are used in different operational departments. For example, in the planning department, power flow optimization problem solver commonly used, while in the department that in charge of control design, electromechanical trained simulation tools, electromagnetic hybrid simulation tools are commonly used. We can find more examples. For example, equipment manufacturing is relatively independent of power system operation. Equipment manufacturers usually use small-scale electromagnetic trained simulation tools or hardware-in-loop electromagnetic trained real-time simulation tools, while power system operating department usually use electromechanical trained simulation tools, electromagnetic hybrid simulation tools, or large-scale electromagnetic trained simulation tools. But under the background of new power systems, the coupling among various operations is greatly enhanced. For example, I just finished a program in which we needed to do offshore farm planning, but we worry about bad planning or cause some wideband oscillation in real-time operation. So we need to do risk assessment of wideband oscillation for the planned result. So usually, I mean, in traditional planning, we don't do electromagnetic simulation to assess wideband oscillation risk. But in this program, we have to do the wideband oscillation scan to make sure the system is safe, is wideband oscillation free. You can see here the planning work and the operation work actually get more connection. more connections. In a word, under new power system circumstance, simulation tools are required to support multiple businesses, be able to seamlessly integrate it within complex business process and support cross business cooperation. All those above challenges make us think whether the simulation tools we are currently using suitable for the research and operation of new power system. So we move our focus from traditional power system to digital twin technologies. If you go to any search engine, such as Baidu in China, we can find a definition about the digital twin. Here, I just quote the definition from the search engine of Baidu. It says digital twin is multi-disciplinary, multi-physical, multi-scale, and multi-probability simulation process that make for use of the physical object model, sensor update, operation history, and other data of the object by mapping the object in virtual space. The whole life cycle process of the object is reflected. If we just take the keywords out, we can see digital twin is a simulation process. That's the main idea, but there are many other, restricts to the simulation process. In the past few years, the number of published papers related to digital twins has dramatically increased. Here, this picture shows the annual trend of the number of publications on digital twins indexed in CNKI. This picture shows the annual trend of the number of publications on digital twins indexed in EI. This is the research field distribution of SCI papers on digital twins. You can see mainly on engineering, computer science, instruments, instrumentation, telecommunication, automation control systems, and so on. Here in China, it's widely accepted that the idea was, the digital twin idea was firstly proposed by Professor Michael Griffiths of University of Michigan in year 2002 for product lifecycle management, which was not called digital twin at that time. Professor Griffiths at that time called the idea mirrored space model. In year 2003, he started to using digital twin in his PLM courses. In year 2014, he published a book, and in this book, he gave a detailed description of digital twins. I saw on the web, there's a lot of people they don't agree that Professor Michael Griffiths proposed the digital twin concept. They believe that the concept of digital twins has a different origin, such as Lhasa first proposed. Some other guys proposed an idea in Lhasa, proposed the digital twin idea. Actually, different people have different understanding about DT. For example, ANSYS Incorporation think digital twin is a simulation model. It's just a model. It's not a simulation process in the digital twin world that has exactly the same operating performance as that of the real world system and can realize real-time simulation, but use the sensor data installed on the real system as the boundary condition of the simulation model. The system in the real world and the system in the digital world can run simultaneously. This is the idea. This is the understanding of Lhasa, who thinks the DT had besides the simulation process, digital twin is also a simulation-based system engineering. Why do different people have different understanding about digital twins? My team and I thinks a lot, and finally we think it maybe because of this. Actually, there are several concepts pertaining to digital twins. The first is the model corresponding to a physical object in digital space. The second is the cyber-physical system composed of a physical object and its digital twin, which maintains synchronization, parallel inference, and closed-loop interaction. The third is the technologies relate to the construction of digital twins of physical objects, such as simulation, analysis, prediction, and control decision based on digital twins. People use digital twins to refer to the above different concepts in different contexts. Is an important reason for the ambiguity. Of course, that's my understanding. I use the following 4 words to conclude the relationship between physical entities and their digital twins. That's autonomy, synchronization, interaction, and symbiosis. Autonomy means the physical twin and the digital twin involve independently. Synchronization means the 2 entities are always at the same development stage, driven by the same internal genes. That means they follow the same fundamental physical laws. Interaction means the 2 entities have impacts to each other, and symbiosis means they are mutually beneficial. The Oracle in one of its report proposed the main features of the physical digital twin system. I think I quite agree more. So I just quote the 5 features here. The first one is visibility. Visibility means the digital twin system, the physical digital twin system allow people to see the operation status of machines and large-scale systems from a digital perspective, so as to achieve real-time monitoring and efficient management of machines and large-scale systems. Predictability means the CPS system using use physical mathematical modeling techniques and the latest sensor data. It's possible to predict the future state of the machine or system, enabling state-based operations and maintenance. The third feature is simulability. It allows operators to input different assumptions into digital models to simulate unrealistic situations in real life, thereby obtaining a true reflection of the machine in some extreme cases. The third feature is interpretability. It allows operators to understand the behavior of individual machines or groups of machines and make reasonable explanations for machine behavior from mathematical models. The last feature is interactivity. It means mathematical models and physical entities can be connected to enable optimal decision-making and execution on the one hand, and collect physical feedback and update mathematical models and decision instructions on the other hand. In China, there are many programs. Those programs are usually call them digital twin programs, but actually not all of them fully reflect or have the 4 features. From the above description, we can have the feeling we will have the such a feeling that the core of digital twin technology actually modeling and simulation. Actually, a Chinese scientist, Professor Lu Qiang, who is my PhD supervisor, Professor Lu published a paper in year 2000. In this paper, he proposed the concept of digital power system. Actually, the idea is exactly the same as digital twin. So some people, I mean, some students ask why the digital twin, the phrase, the idea is not proposed by Professor Lu. I mean, the word why doesn't Professor Lu use the phrase digital twin to express his idea? I'll talk about this later. Professor Lu proposed his idea even 2 years earlier than Professor Griffiths. In China, I mean, there's also a lot of people keep asking what's the difference between traditional power system simulation and digital twin technology, especially people from engineering side, field engineering side. To answer that question, we have to do a brief historical retrospect. Actually, in 19 I mean, power system start to utilize simulation tools as half centuries ago, because in 1995 the Great North American Power Outage shocked power engineers at that time. So a lot of researchers started to work on power system, try to understand power systems and to try to do some decision making work. In 1970s, the energy management system was born. That's after the American power, the great North American power outage, including functions such as energy management, network analysis, and dispatcher training. From then on, people using simulation as people start to use simulation tools. I mean, widely. But even today, power engineers are still reluctant to conduct closed-loop control for power system, even they know they must do simulation, because the dynamic process of power system is too fast and power system dynamics are too complex, and the cost of power system blackout is too high, and our simulation cannot make the topologies, the parameters of their models exactly the same as that of the real system. And power engineers know their simulation results have some errors comparing to the real systems. So they cannot fully understand the results. So they need to close the control loop, by themselves. So that is a kind of people in loop control. On the other hand, the dynamic scales of power system are widely distributed. It's hard to build a whole model to describe all dynamics of power systems. So power engineers are very smart. It's a common practice that they build different models to describe dynamics in different time span, and different simulation tools are developed for simulating dynamics with different time scales. That's why I think Professor Liu didn't use digital twin to describe his ideas of digital power system, because you can think about this even on the street. You come across two peoples, they have exactly the same eyeball. You don't think they are, you won't think they are twins, because any simulation tools of power system can only simulate the system in a certain time span, certain time span and a certain area. How to construct the physical digital twin systems according to the concept of digital twin and the digital twin. We think we have to follow 6 steps. First step, we need advanced measurement infrastructure. Then we need to transmit the measurements to the digital space through a communication network. Then we need to establish a mathematical model of the physical system in the digital space, and integrate it with measurement data. The fourth step is to analyze the physical world using the established mathematical model, then make control decision based on the analysis result, then feedback the control signal to the physical world. Today, new power system security and stability analysis and control method based on traditional simulation face a lot of challenges, such as modeling inaccuracy affects mechanism cognition, the processing efficiency, of massive simulation in order to cope with randomness as no contingency control strategies based on preconceived scenarios lack robustness, and so on. So we think the digital twin technology may help because the model accuracy of the digital twin is ensured by the mechanism data hybrid-driven method and iterative correction simulation strategy of synchronous evolution of digital physical twins reduce a large number of uncertain scenarios. And online policy verification based on the digital twin ensures the effectiveness and robustness of control policy. So we draw the conclusion that the digital twin technology seems more suitable for analysis and control of new power systems. What's the difference between the traditional power system simulation and the digital twin? Here, we think we can answer the question from the function point of view. The traditional power system simulation is just an analytical tool. Digital twins are application and business oriented. So with the aid of a digital twin, augmented perception, cognition, intelligence, and control can be achieved. A professor named Tao Fei proposed his understanding about the difference between traditional power system simulation and digital twin technology. He used the maturity model of digital twin technology to give a clear description. He thinks he proposed the maturity model with 6 levels from level 0 to level 5. He thinks that the lowest level corresponds to the general concept of digital twin technology, while the highest level corresponds to the ideal digital twin technology. He also thinks that the traditional power system simulation can be regarded as generalized digital twin technology or level 0 digital twin technology, where the physical twin and the digital twin get closed manually. In another word, the interaction between the physical world and the digital world is achieved manually. In the highest level, the digital twin and physical twin, they can interact automatically, and they even can dynamically reconstruct it, and they can, interact it more intelligently. In the level 5, that is the highest level of digital twin technology. Physical entities and their digital twins operates in synchronization over extended periods. And physical entities and their digital twins can perceive and recognize each other's updates in real time based on two-way interaction. Physical entities and their digital twins can maintain dynamic consistency through autonomous construction or dynamic reconfiguration. Also, the cyber-physical system can ensure the effectiveness of various of functionalities such as visualization, prediction, decision-making, and optimization. Next, I will introduce our practice in utilizing digital twins to advance the research of new power systems. Because the core of digital twin technology is modeling and simulation. So it's natural to ask if we can build the physical digital twin system based on traditional simulation tools. Considering simulation is a mean, not an end. Simulation must serve operations. So we think constructing physical digital twin system needs new tools. But what kind of tools do we need to construct a physical digital twin systems? Given that a typical business process consists of several key components, simulation plays an essential role in the operations of power systems. So we need to look into the power system business in detail. For power system business, for example, planning, usually we need to use some simulation tools. And in these simulation tools, we need to build models for power systems. For example, we may need to build a steady-state circuit model. We may need to build some other models. We need to conduct power flow calculation. We need to conduct electromechanical trend simulation and so on. For different businesses, we need to build different models, and we need to develop different algorithms to conduct simulations. Inspired by mobile internet applications, where an application usually consists of several services or other applications. For example, the popular app Dianping or China's Yelp has functions such as searching, sorting, mapping, phone reservations, taxi hailing, bill payment, and reviews. These functions may be provided by different companies and can be used by other apps. The owner of Dianping may try and complete, put those functions together and create the app. So we think if we decouple the models, algorithms, and applications and develop a powerful middle platform and dispatching center, then we provide third-party developers convenient and flexible SDK. And then we just need to build an open app ecosystem. Then we may have a tool or environment that supports constructing digital twins for new power systems. In the past decades, our team dedicates to develop a tool that facilitates application of digital twin technology, namely Cloud PSS X Studio, a digital twin workshop for energy and power system. It has a 5-layer structure. The most bottom is basic hardware platform. Above it is the basic environment, including operating systems, database, and so on. The third level is the function kernels. We provide some native model or some core, some native functions. And the fourth level, we provide some develop kit, including the Sim Studio, Funk Studio, and App Studio. I already explained their functions later. Then use the underneath 4-level abilities we can develop, meaning high-level apps, advanced apps, such as high-performance electromagnetic trend simulation. We call it Cloud PSS EMT Lab, Digital Twin Lab for Integrated Energy System. We call it Cloud PSS IES Lab, and so on. Third-party developers can develop their own apps. If we compare Cloud PSS X Studio with other software, the lower 3 layers act as an OS. The middle layer can provide functions as MATLAB, PSCAP, LabVIEW do, and the top layer is just like App Store. In another word, called PSSX Studio are hardware and OS productivity tool and application market for digital twins of energy and power systems. The developed kit includes 3 handy tools which enable third-party developers to develop advanced digital twin applications. This tool is free on the web. Everybody can access through this website. The Sim Studio allow developers to easily construct and manage digital twin simulation models for energy and power systems. Nowadays, we have many building models such as and cases such as AC/DC power grids, integrated energy system, distribution system, and circuit system. Developers can create their own advanced simulation applications with Sim Studio SDK using their most favorable computer languages. Funk Studio allow developers to seamlessly integrate digital twin computation core of energy and power system in PSS. App Studio enable developers to build digital twin applications for energy and power system. To use the X Studio, there are 4 steps. In the first step, people need to build the energy power system model. Then write algorithmic kernels and integrate in Funk Studio. Then design UI and visualization panels in App Studio. Then bind the data and events in App Studio with functions in Funk Studio. Then after debugging application preview, then you can release the app. Actually, my student and third-party developers has built dozens of digital twin applications or simulation applications. Here are some examples. This is a parameter optimization platform for power system electromagnetic trend simulation models. It has functions such as electromagnetic trend simulation, transformer in rush, current parameter optimization, new energy controller, parameter optimization, generator, parameter identification, those kind of functions. This is another function, the new energy generation, power grid interaction analysis and visualization platform. It can do topology exhibition, sweeping frequency response analysis, digital simulation of wind farms, PVES interaction analysis, emulation of fault alarm, because this is real, application running on power company. So we have to obfuscate the data and to desensitize it. This is another application, which is feasibility analysis of Nongpan water lifting project. It's a microgrid. But this independent system is huge. Use PV energy to lift water and watering planet. It has, platform. This app has functions such as dispatch optimization, fault analysis, protection check, multi-scenario analysis, boundary condition check, system capacity check, blackout strategy optimization, and so on. Okay, I just skip those apps. There are so many. CalPSS also support college student innovation competition, a team using Cloud PSS won the first college electrical and electronic engineering innovation contest special prize. Now it's Tsinghua campus public software, and it's also adopted in experiment course by School of Electrical Engineering, Shanghai Jiao Tong University, and some other universities. I want to show you another project. This is a project. Let's see. I'm sorry, it's in Chinese, but this project is fully represent the 5 features of physical digital twin system. Actually, this project is to monitor the energy cost of a HVDC station. Xi'an Jiao Tong University, a team of Xi'an Jiao Tong University proposed a method to estimate the energy cost of HVDC station, both the rectifier side and the inverter side. But
Chen, are you showing the another slide now, or
yes, sorry, I forgot to.
I think you should finish
yes,
the current slide and then newly share the another slide, because still I can see only alphabets.
Okay. Do you see the slide?
Yes. Now I can see.
Sorry, it's in Chinese. But I explain it to you. It's a real project. I mean, it's really it's in real time operation. Okay. With the method proposed by Xi'an Jiao Tong University group, if all the parameters, system state can be measured, then we can use that formula, that equation to assess the energy cost. But unfortunately, some parameters and some system state are not measurable. So we cannot use that equation to assess the energy cost. So we build a model, a digital model, or a digital twin for the whole station, and we run the station, run the model in the cyberspace simultaneously with the real system. Use the measurable data to do the parameter identification, to do the state estimation, so we can get all the parameters and system states, so we can use the equation to do the energy cost estimation. Then we do the control decision and verify the control to see whether those control can decrease the energy cost. If they do, I mean, the strategies really decrease the energy cost, then we apply the strategy to the real system. So that's a digital twin project. This project is equipped in real site. Here is some computers, the workstations, Here is the UI, the interface. You can see here the models, the HVDC station models. This is system model. This is the inverter model. I mean the switch model. Here are the equations for calculate the energy cost. So this system has been equipped in the station, which is located in Wuhan, Hubei province, here in China. Another, the sending end is in Shanxi province, here. This is the location of the HVDC line. Okay, let me back to the.
Yeah, thank you very much for the very informative and then also very advanced research related presentations. So the folks, if you have any questions, please use our like a chat window and then type your questions, and then the speaker Chen Shen can read your questions. But beforehand, I have just one or two quick questions. So yeah, actually, when we started talk about digital twin, my feeling was that the definition really depends on the engineers. And so the Japanese EPRI also launched the digital twin research studies. I think they started more than 5 years ago and still ongoing. And then what they are doing is to get all of the measurable data, and then based on that measurable data, they establish the like a dynamic model. And then, as you said, there are some like unmeasurable quantities, and then also some parameters are not known. So based on the real-time measurement data, then they have a better guess for unknown parameters.
Exactly.
And then they the periodically update these parameters as time goes.
Yes.
And then, so that is, the Japanese EPRI's final goal, because the model parameters are time varying, always changing.
Yes,
then-
yes, that's the most hard part. Because the system usually used in normal situation, you didn't see much the disturbance. So you only see the system states with noises, right? With measurement
right, yeah.
noises or some other noises. So you have to from those data, normal operation data, to identify, to see, to tell whether the system parameters has changed or not. Though that's the most part.
Okay.
My student is working on that. Try to use some new the parameter identification method to do that.
Okay, so if we have like a unmeasurable data, and then if we do not have like a perfect high fidelity model, and then in this case we cannot help relying on a kind of black box model. And then the typical one must be like for example, utility scale or PVs or wind farms, I guess, because usually the parameters inside and the internal parameters of the inverters are kind of confidential, and then usually the vendors do not disclose these parameters.
Yes.
And then even EMT models are available. Currently the vendors provide only like a dynamic link libraries only, which means we do not know the internal parameters at all. And then in your digital twin platform, can you identify or estimate the internal parameters of the inverters one by one? Is this possible?
if a complex system, I only have black box model, definitely I cannot. So in our project, the HVDC project, actually we have the white box model. The vendors actually provide us the whole model. Of course, sometimes we just the system is very small. It's not. I mean, the scale is not very big. I mean, the physical entity is just a small part of a big system. At that time, we may be able to estimate the data parameters for the model. For example, today's wind wind turbine. Usually the wind turbine manufacturers, they don't provide us with their white box model, but usually their model even is black, but they follow some common control logic, and we just use that the common model to represent the real black model, and we try to tune the parameters of the common model to make the output as close as to the real output of the black model. Of course, there are some errors. That's why theoretically we have many work to do. For example, if the digital twin has some errors to comparing to the real world. How can you guarantee your control is robust to those errors? Those kind of work actually need to do a lot of theoretical research.
I see. Yeah, actually, the portion of them must be exactly what the US engineers have done. So, as I said, we have generic EMT models for inverters.
Yes,
And
yes.
then, so as I said, the vendor specific model is not the same as the generic inverter models. Then what we have to do is to map all of the detailed parameters of the vendor specific models into the generic model. So that's a very time consuming task. And sometimes it's easy, but sometimes it is not at all easy. That's a kind of challenging part, even in the US. But the US is a big country. But when I joined the EMT workshop organized by Oak Ridge National Laboratory, that is the DOE funded, government supported laboratory, we covered what area of topics like attendees are not only from how to say the vendors, but also the DOE the government officers and so forth. And then also the engineers are not only from Eastern Interconnection, but also WCC. So probably my information is somehow like a US wide like a kind of common sense, I guess. But when we joined the Sigray working group, we were talking about the event-based emergency control for transient stability, right?
Yes,
So
yes.
that for that part, they capture the system status using the sensors. And then based on that snapshot, we run hundreds of contingency analysis. And we can predict which contingency is critical. So do you think that event-based control is also a portion of the digital twin?
Actually, I think yes, it's a portion of digital twin because here we think the digital twin is not just one. You can generate many digital twins. Some twins just do the what if scan. some twins, they may do some other things. So I mean, our idea is not limited to very strict, boundaries. So we just we understand that the digital twin just means you can generate many digital models in cyberspace, and you use different twins, digital twins, to do different work. That's it.
Okay. Well, I think we have one people who raised his hand. So, yes, Sky, you can speak out.
Dr. Chen, can you hear me well?
Yes.
Excellent. Question for you on the model building. That seems to be a critical factor for the digital twin.
Yes.
And if you're missing parameters that are just simply, I might be too ignorant to know that certain parameters are required that I am not measuring, but that
Mhm.
I suspect that this will show up in deviations of the simulation from the actual plant in progress. Is that true?
Yes. Mhm.
Okay, so given that is in some systems, it may be extremely difficult to find out what those parameters are. Is there any I don't know, it would to me it would be magic that it can identify something that would tell me where to look for parameters that are not identified. The process is varying in some way, and you should look in this part of the model. Inverter 7 seems to be deviating from the model. Is there any way to backtrack? Is my question. Is there any way to backtrack from the deviations of the simulation to identify the culprit with an or the parts of the model with an incorrect formulation?
Good question. Actually, before we do this, we need to do some theoretical analysis. For example, the project of the HVDC energy saving project, and we have the equation, and we study the required parameters, the states, to see whether we can measure it. If we cannot, we just to see from which parameters, other parameters, states, can we just guess or trace the parameter change. So it's an observable problem, or whether it's identifiable problem. And to identify online or estimate those parameters, at least we need to do how many other measurements, whether those measurements or whether those parameters or states are measurable or not. If not, we have to put more sensors to do it. So it's an iteration work. We need to do a lot of pre-work to really realize our idea.
My concern is that will work fine for steady state or commonly occurring situations, and you'd like to use the digital twin to go outside normal operations. And that's where the model will fail, because we don't have a full understanding of the process. Right when we need it the most, in other words, to handle emergency situations, it will fail us. And I fear that that's going to cast a lot of doubt in the use of the digital twin, because its primary purpose for many people would be to emergency response. And that's where it failed.
Yes, I agree. But we must know our models. I mean, the digital twin, the range of the usable range for the digital twin. If we realize the real situation has changed dramatically, the digital twin, I mean, out of the usable range of the digital twin, maybe we just, stop using the generated, control strategy for normal situations. So that's also a very critical, conditions we must realize for use the digital twin. I totally agree. We still have a long way to go for
Well,
those.
Dr. Shen,
Mm.
can the digital twin identify when it is out of bounds and say and then flash on the screen, do not use, do not use, do not use, because is that something that's only theoretically possible, or is it actually possible?
That's possible. Well, we do that. You know, you have a digital twin, so you can predict the system states in future. That means you can use the digital twin to look ahead for a certain period of time. If then you use when the time time is coming, you just compare the measurement with the predictive the simulated predicted results. If the error becomes large and large and exceed some certain range, you may realize the digital twin is not usable. The error is too big. So
Thank you.
today we are doing this.
Okay,
Sure, you're welcome.
Okay, I think the time is up. So our next webinar will cover the same topic regarding digital twin in November. And we're going to invite an IEEE fellow from Greece, Nikos Hatzichagigio. I don't know if this pronunciation is correct. But anyway, the date and time are November the 12th, 1-2, and starting at 10 a.m. our time. And I will upload a flyer shortly once it is ready. And then please stay tuned and enjoy the rest of your day. Anyway, once again, Chen Shen, thank you so much for the nice presentation today.
Thank you, Koji. Thank you,
And-
everybody.
Yeah, bye for now. Thank
Bye.
you.